So here's this equation. This equation comes right out of the textbook, and in fact, last week we did the part that didn't have the friction part. It was just the mg sine theta equals max, because we assumed there was no friction. And so my textbook, every physics textbook, this is the first thing right out of the box on inclined planes when friction's there, is getting to this relationship. So I want to talk about the pieces parts, which is going to be largely a repeat of what I was just saying. So let's go right for the throat. The easy kill is recognizing that mg is the true weight. Okay, so we could write true weight. That's what you need to think when you see mg. Mg is the true weight of an object. Its mass times the gravitational field strength of Earth. That is what it would weigh on a scale. When I see, so mg isn't just letters to push around in algebra land. It represents something. It represents the true weight of an object with mass m. Okay? Now, as I was saying before, sine and cosine, they're just some fraction. Now, obviously, they're going to be a different fraction unless the angle is 45 degrees, okay? But they're just a fraction. This leg over that leg of the triangle. It's just a fraction. And you don't have to like fractions as mathematical entities. You already know that what a fraction is. It's something less than the whole. It's a part of the whole. And so when we look at all of this together, these two parts, and then we will get to the mu thing, this is some fraction of the true weight. Another way, and I'll write it for the other one, is the apparent weight in some direction. That's a little bit less obvious, in my opinion. Just the simplicity, the general thing. Here's this fraction called sine, and here's this thing called mg called true weight. So this is whatever this is, it's some fraction of the true weight. Technically, this one would also be the apparent weight in some direction. It would just be in the other direction, be it parallel to or perpendicular to the direction, the ramp. So we put words to the math, and there's one more math thing to address, and it's this mu thing. And so remember that mu was defined as the friction force over the normal force, or we get friction equals mu n. So the friction force is some fraction of the normal force, and the normal force is mg, all right? So this is harder. So, the mg sine theta was easy because I kept it some fraction of true weight. Doesn't get any simpler. Mg cosine theta, I could also call it some fraction true weight, but I wanted to give the other layer of it's the apparent weight, but it's only part of the apparent weight. These two terms, minus, if I didn't have the mu, would give the full weight. If I added mg theta to mg cosine theta, I'd always get true weight. Always, in any setting. I need more coffee or something. All right, so what could I call mu? And that's a little bit more different. And It is also a fraction. It always comes in a decimal between 0 and 1. And what I'm going to call it is some fraction, because it is that. Okay? But it's going to be what it represents an average reaction force. But remember, it's just a number. But it's a number made up of forces. It's a ratio of forces. And so friction's always taking away from unfettered motion. It makes unfettered motion fettered. All right? It's a pretty basic idea. So I hope this helps, even if it just helps a little bit, clearing up how math connects to the reality. Because there's, that's a lot of symbols to push around. And you'll need to push them around. And the more that you have a storyline that goes with the symbols, the easier it is to do the math. Because the math is technically trivial. You survived algebra, pre-calculus. This is not high-level algebra at all. But it is more visually assaulting than what you had in pre-calculus, most likely. Because the rules that you learned in math class, while they apply here, it's a different set of problems. And there's a lot of baggage with those problems. And the fortunate thing is that the baggage is something that will help you make sense of the math. At least it has that potential. There's almost no hope that you can make sense of math in math class. You can learn the rules and master them to some degree, but making sense of them, there's honestly hardly any time for that. I've taught those math classes, and as much as I would love to reform them, it would take twice as long to reform them in a way that would also provide understanding, because that context, you can only understand math in the context of what it was made up for, which is science. So, I think I've said it before, if we were smart, you would have 4, 5, 6 years of integrated math and science where you would build the math you need to do a science answer. And it would take you 4 years to finish this course, but that's because it's embedded in. In fact, the way that science was built, there was no separation. And that was something that happened, began about 100 years after Newton. They started to send science and math on separate academic paths. They used to be fully integrated. But there you go. Progress, yay. So that, I wanted to just get out an English translation of this ugly equation. And I think another cool aspect of this is really, I still have Newton's second law here, F equals ma. It's still just F equals ma. Pretty much everything boils down to that in physics. And sometimes the details get a little messy, as seen here. All right, so this is just ma. All right, so there's that. And now I want to do another clarity-making exercise here. You had some notes, and you'll have some problems on an Atwood machine, but the Atwood machine that you're going to be required to solve for is far simpler than this one. And the goal here isn't to do a bunch of complicated math. The goal here is to see how the zeroth law way of thinking and the math that is demanded by that, which is just obeying the laws of physics, helps us solve a complicated part of what is an even more complicated problem, okay? And we're only going to do the setup part of it as a way to connect the force and energy part of this puzzle with the kinematic stuff we've left behind. Well, we haven't left behind, just we're more focused on forces. So these A and B are pulleys, okay? And I wished I had drawn it, but I'll have to do it now. Assume that A is connected to the ceiling, okay? So A is up there on the ceiling, and it's not moving. A is going to stay in that spot. So the middle of pulley A is going to be sort of an upper, it's our 0 point for length, because we got these ropes. So the white vertical lines are ropes hanging over that pulley, which I've drawn as though it has a groove, so you can't see it going over the pulley. And the pink weights are masses, mass 1, 2, 3, etc. And we're going to, for the sake of this discussion, mass 1 is the biggest weight, which means as soon as you let it go, it's going to start pulling B up, and M and 2 and 3 are bound to move as well. But what's going to happen is various portions of the rope lengths are going to start changing, and we want to track that. And that initially seems messy, so I'm going to put a line here that's kind of capturing the top of mass 1. I'm going to put another line through pulley B because it's going to move from that position. It's going to start to go up and there. And then that means if mass 2 starts moving and mass 3 start moving, that they're where the top of those boxes go, which is where I put this fat line because it's easier to draw than a dotted one, we can measure that. And so there's 4 changing string lengths for 2 string lengths. All right, so if we're talking about this rope here, then I could say, all right, I'm going to call this length here, I'm going to call it Y1 because that's the one associated with M1, which is on the left side of pulley A. I'm going to call this one, we'll call it YB because it is the length of the string associated with the right-hand side between A and B. And so as B rises and M1 falls, Y1 and YB are going to change, all right? But here's the thing about this length of string A. So if I have the length of string A, it's comprised of 3 parts. It's the length of Y1 plus the length of YB plus half of the circumference of the pulley, which is a circle. So 2 pi r is 1 full circumference, pi r would be half of that. Length A, the total length of the string, is constant. Right? It's not like it's going to lose or gain string length, okay? That has to stay constant, but Y1 and YB are going to change. Pi r won't change. So here's the subtle thing that would be easy to miss in reading and easy to miss in listening to a lecture. So this next 30 seconds or so, most important part of the puzzle so far. Something's going to change in the system. If I let mass 1 go, stuff's going to start moving. And so I know the laws of physics say the position or these component links, they are going to change. And so I need to ask myself, what is the change in this function? And so I can use delta, difference. We use that as this minus that, final minus initial. What is the change in this length of A string function? Okay? Because I know it has to change. So this is, I don't know if we've ever formally named the law of change, but there's no scientist worth their weight in water who would deny that things in the world are changing, and that's what science pays attention to, okay? Whether it's biology, chemistry, physics, medicine. If it's in the world, it's changing, right? So now I could transform this idea of change, or I'll call it law of change, now leads me to a mathematical way that's reminiscent of what we've been doing. In fact, it's exactly what we've been doing. Now, this next, because the law of change says, okay, there's going to be a change in these quantities. Now, we could ask ourselves, what's going to be the change in the length of A, the whole rope? Well, we know that's going to be 0. We don't know what delta y1 and delta yb are going to be, but we know they're not 0. They're going, and in fact, if one gets bigger, the other one gets smaller by the same amount. We know that much. It has to be that way. And we know that the curve part, that's the change in that half circumference, that's not going to change. It's going to keep being one value, whatever pi r is. So the change in that thing is 0. So now we could write delta y1 equals the negative of delta yb. Or we could say their sum is 0. In fact, I think I'll do that. So, okay, guess what? We probably could have just gone straight to that. But if we did that, we would be assuming that all of that thinking about the law of change and how to represent it mathematically was fully understood. And that's not always true. You know, as soon as you have more than about 3 people, guarantee you one or more of them, that's not something that was in their head when we wrote it down. Okay? So it's about modeling. It's not about memorizing facts. Okay? So here we have this, and then, wait a minute. First zeroth law tells me that every change in position, which is what I just wrote, delta y1, there's a change in position there, it's a displacement, is always associated with a change in time. So the first zeroth law is another change law that's very specific, in that when you have a change in position, it absolutely always, everywhere in the universe requires a change in time, and it's always a change in position per change in time. They always are connected in that way, per that kind of thinking. Well, we know what delta y, a change in position relative to time, is a velocity. So this is really Vy1 plus Vb. The sum of those two velocities equals 0. Because 0 divided by anything is 0. You're like, wait a minute. Now I have a speed relationship that I got from the length relationship. Those of you that have had calculus, or will, we just did the first derivative without doing calculus. So the zeroth laws, because they're change laws, and because calculus is in mathematics of change, the laws of physics demand calculus. And you don't always have to do calculus in order to do calculus. We're like, wait a minute. These speeds are going to change too. And now I need to wonder, okay, what is the change function for speed? And so you would write delta Vy1 plus delta Vb equals 0. And you're like, The second zeroth law demands that every change in speed also requires a change in time. Well, a change in speed per unit time is an acceleration, and the sum of those accelerations equals 0. So the downward acceleration of mass 1 and the upward acceleration of pulley B, those have to be equal. That's the only way they could be 0, which means one is the negative of the other. Now, this is just part of the puzzle, and I'm not going to do the rest of the puzzle because the goal isn't to actually solve this complicated problem, because it's a bit more than this course requires of you. But this part of the puzzle is one that lets us go all the way back to the beginning of the course and tie in this fundamental idea about change, and in particular, the Zeroth Laws. So the Zeroth Laws are the fundamental way to encode for this larger law of change. Okay? And so I would love to sit down with people who have different kinds of expertise than me, say chemistry, biology, and come up with their first and second Zeroth Laws. Because I don't care what branch of science, biology, chemistry, etc., we all have these very fundamental things in that craft. And there you go. So just to, so that's one piece of the puzzle. Now, we got to this answer of acceleration, which is important because guess what Newton's second law has as one of two factors? Acceleration. So Newton's second law is something we can't avoid with force analyses, and we must have a way to account for acceleration. We just did that with lengths of string and the Zeroth laws. Now we would have to continue and come up with another set of equations. Whoops, that's not the one I want. Because now there's going to be this y2 and this y3. And the other thing I didn't say is it's really important that there be a common reference point, which is why we chose the non-moving A as sort of our 0 point. All right? And so if we were to repeat this analysis for the B string, so I should have brought my guitar, the A string and the B string, all right? We would have a slightly more complicated set of equations because now it's going to be the difference between y2 and yb and y3 and yb. So it still is going to work out to a slightly longer acceleration formula, but we would be able to account for all the accelerations. So that means if we went to go do force analysis, we would have a way to have our A with all of our M's and pair them up. And let me tell you, it is a bit of an ugly algebraic thing. I'm going to show it to you, but I'm not going to work it all out for you because it's not important.